Dear all, good morning. We are about to start our tutorial privacy today, and we are waiting just a couple of minutes, I think, to wait for some other attendees to come remotely and physically, and then we will start. Okay, here we are, and without further ado, I can give the remote stage to our first speaker today, who is Tommaso Di Noia.
And in this tutorial. Today we will talk about this pursuing privacy in recommender systems with the view of users and researchers from regulations to application. This tutorial will be presented by a bunch of people. You will have Yashar, Claudio, Antonio, Lucio, Walter, and myself from Politecnico di Bari. And we are very happy that also Luca Belli from Twitter is within the presenters of this tutorial. You know, the contribution of Luca is particularly important because he will talk a bit about also all the problems and issues related to the Twitter datasets released for the RecSys challenge last year. So it is something that is both on the industrial and research point of view. This is the table of contents for today. So for this 3-hour tutorial, so we'll start with I will start with an introduction of the problem. You know, the main issues related to data privacy and specifically how these problems are related to recommender system. Maybe this is something that we already know, but you know, it is interesting to see these issues from a regulatory point of view. Then, you know, Yashar will move to learning paradigms and threats for privacy-oriented recommender systems, and then we will introduce you the techniques for privacy preserving in machine learning. So once we have, and you know, we'll talk about the differential privacy, cryptography, and similar topics. Once we have this introduction to privacy in machine learning, then we can move to privacy in recommender systems. And there we'll see a trending research and open challenges. Then we will have the speech by Luca for the case of Twitter. And finally, we will have a hands-on session where we will show you how to play with this privacy stuff within your recommender systems algorithms. Okay, so let's start this introductory part, and let's talk about let's introduce a bit the problem related to big data, recommender systems, and privacy. So why these three elements are related with each other. So let's start from the beginning. So this is maybe the first time that the topic big data was the topic big data was introduced for the first time. This is a blog post at IBM dated March 19 in 2012, where they say that every day we create 2.5 quintillion bytes of data, so much that 90% of the data in the world today has been created in the last 2 years alone. So this post was dated, you see, it is from 2012, so it was 10 years ago. We can all imagine the amount of data that we have today, and we are continually creating every single day. Of course, this data come from everywhere, from different sources, with the different semantics, sometimes with a different also syntax. But the point is that they are collected, and they can be exploited to provide new services. And this is something that we know, because big data is the fuel of modern artificial intelligence applications, and this is of interest to us, of recommender systems. So we all know that we are going to provide new services for personalized medicine, for example, by using patient records. So we all know that all the entertainment services are full of recommender system, as well as we expect that in the near future, new recommender system services will be provided to citizens, since we have this new smart cities where data related to the city environment are collected and can be used to help the life of the citizens. While all the problem related, all the applications related to personal data and home automation. But, and this is clearly not a secret, we do know that data privacy is an important issue when we when we use these services, when we collect this data, when we exploit this data to provide services to the end user. So this is something that we do need to take care of, and when we design. And also when we implement our system. Well, actually, also when we collect data to design, to train, our system, and design and implement and deploy them. The problem related to privacy in AI systems, and then also in recommender systems, is something that the European Commission is really aware of. And I'm just showing you this document from 2018. This building trust in human-centric artificial intelligence, where within this document, the European Commission proposed 7 key points for trustworthy artificial intelligence. And the third point out of the 7 is related to privacy and data governance. So within this document, it's clearly stated that privacy and data protection must be guaranteed at all stages of the AI system's life cycle. So from data collection up to data exploitation, and then when the system is running and the system has been already deployed. And then they also say that to allow individuals to trust the data processing, it must be ensured that they have full control over their own data, and that data concerning them will not be used to harm or discriminate against them. So this is particularly important for us as within our RecSys community, since we really use a lot of personal data. So this is something that we have to really take into account when we design our systems, our recommender system, because again, all the data that we collect are all data that somehow are the basic elements of our user profiles. But this is something not really new, because already within the GDPR there are specific elements related to protection and control of individuals' personal data. And there are also some fines that you have to pay in case your data is breached. And you know, the total amount can be also quite high. Also, within this European General Data Protection Regulation, the individual's rights are clearly stated also in this case. And you know, here we see just a few examples about these rights. And it is the right to access the user data. So are my data collected and processed? Why? How long? So these are all the information that users must have when their data are used. And then there must be the right to rectification, erasure, and restrict processing. So again, this is something that from a regulatory point of view, it is already there. So it is something that we must take into account when we consider our systems. And as I was mentioning before, this is particularly important for recommender systems because you know, with recommender systems, all the data that we collect are user-centric data. So all the data that we collect are data which are built around users. This data are related to their preferences, their check-ins. Also, we can have sensitive information. We can have sensitive attributes such as you know, the gender, religion, or something like that. That can be something really harmful if we do not manage this information properly within our systems. And you know, I was mentioning before personalized medicine. So also in this case, what we are going to witness in the next future is the proliferation of this personalized systems for healthcare. And in this case, all the data that we use are definitely sensitive data because they are data related to the health of the user. So we have medical records or even genomic data. So that's why specifically in our case, privacy is a key point, and it is something that we must consider. Also of the Recommender Systems Handbook in its second edition, there is this chapter on privacy aspects of recommender systems. So what they say is that, what they clearly say is that there exists this privacy personalization trade-off. So what does this mean? So this means that we clearly know that whenever we build our system, the quality of the final result is strongly related to the amount. So how much data do we have, or how much this data is rich, and how fresh is this data? So how frequently this data is updated. So the more and fresh and rich the data we have, the better the recommendations. But it is clearly understandable that these are exactly the same critical aspects when we talk about privacy. So if we have more data, if we have other data related to the user profile, so if we can put together and we can integrate data from different sources, and so by using some side information, for example, or if this data is continually updated, well, this is a clear problem, and this is a clear risk for the privacy of the users. So within the same chapter, there is this very nice classification of privacy risks, and you know, they classify these risks starting from the possibility of direct access to data. So sometimes what happens is that we can have applications collecting more data than they really need. So for example, there could be the case of some applications for music that they also collect information about you know, your geographical location, or where you are and where you move, if you stay within a place for a longer time and something like that. So apparently this information has nothing to do with music. So but the point is that since you know, storing data right now is quite cheap, so we do know that storage is something that is getting cheaper and cheaper. So companies sometimes they tend to collect you know, as much data as possible, because you know, in principle they could reuse sometime in the future this data. Well, actually now with GDPR, especially in Europe, this is, really, you must be very careful when you collect this data, but, sometimes this still happens. And since we have all this data, for most of the recommender system architectures that we have right now, all this data are stored in a unique place. So we have a centralized repository. So of course, this is a serious problem. We will see in the next slides that we are quite lucky because some federated and decentralized architecture are coming. The other risk is that when we share data with third parties, this is not necessarily the case of companies selling data or sharing data for commercial purposes. We will see that, for example, there are famous cases where this data were shared for research purposes, but there was an incredible privacy problem with this data released by these two big companies, and I'm talking about American Online and also Netflix. And finally, we do know that we can have direct access to data from some employees. This is something that is quite hard to control. So sometimes we can have that employees within company can access personal data, and also in this case, we can raise a serious privacy issue. So these are the two cases I was mentioning before. This is maybe the most famous case of, one of the first famous case with the privacy related to some data released to third parties. In this case, American Online released this data set with the search logs of users. Of course, everything was anonymized. So they did not release any personal information about users, but they released information about their search logs, basically. Well, there was this nice article by the New York Times where they show that by just combining this data with other data and combining this data within the same data sets, as well as by looking at the search for a single user, it was possible to clearly identify the real user in this case. And this Thelma Arnold became quite famous because of this. Well, actually, she agreed on revealing her identity on the New York Times, but just to show that it was possible, even if we have anonymized data, to get to identify the right person. And this is exactly what happens also, and this is something that we know maybe within our community. This is something that happened with the Netflix prize. So Netflix released this data set, and everything again was anonymized, so there was no information about the users, but the point was that this information was somehow encoded also within some publicly available data sets. So by combining, in this case, the data from Netflix, the data set from Netflix and the data available on IMDb, then it was possible to de-anonymize this data, and then it was possible to identify people within the original data set. So this is one of the main reasons why we, Netflix did not go for the second challenge, basically. Going back to the privacy risks, within this classification, we can also have these privacy risks related to the inference from user preference data. So we collect this data related to the user profile, and sometimes some sensitive information is not explicitly stated within the data, but we do know that by using some machine learning techniques, we can somehow infer new knowledge from the knowledge that is encoded within the data. And of course, this knowledge can be sensitive knowledge related to the user. We don't need to have a specific attribute. We can, for example, we don't need to have a specific attribute on the gender, for example, but we can also have, for instance, what we call the proxy attributes, and by which we can infer this information. So we can have some attributes, and by combining the values within these attributes, then we can infer the gender of the user, for example. The other privacy risk related to this inference from user preference data is that related to targeted advertising. So the targeted advertising is something quite interesting because it can be seen as a kind of cross-domain recommender systems, because you have recommendations in different domains. So given your search history, and since in this case you have information from different domains, it can happen that at a certain point you can have an advertisement that is not related to what you are doing right now in that moment, but it is related to another domain and to something different, different that you did in the past. So also in this case, there is this famous example of this parent who knew that their daughter was pregnant just because at a certain point they started to receive advertisements related to baby clothes and related stuff. And finally, given this information that we can infer from data, unfortunately, we can also have some discrimination, and discrimination that can be due to any kind of information. And sometimes this is not something that we explicitly want. That very often, this is something that we do not explicitly model within the system, but this is something that can happen. Finally, then we have this other class of possible privacy risks, which are the risks imposed by other system users. So this is specific of recommender systems, because in collaborative approaches, we do know that we can compute information and we can understand the user preferences and profiles by looking at the information related to other users. So we compare basically users with each other, and by comparing these users, then we can get some also in this case some sensitive information with respect to the target user, for example. And this sensitive information is maybe something that the user is not willing to reveal. Also related to the RecSys problem, we can also get this information by attacking the system, for example. So we can, here we have just an example where we create fake profiles to identify some user preferences. So what we do is that we create these user profiles, and by creating these user profiles, then we see which are the users that somehow are similar to this fake user profile, and by analyzing this data, we can infer some information related to the users which are similar to the fake one. And finally, we have that by observing what changes in item-to-item collaborative systems, and by just passively observing these changes, we may infer preferences, and also in this case sensitive information about the user. So, for example, if you consider the Amazon who bought this or who observed this item also observed these other items. So suppose that you already know a few items, just a few items rated or observed by a user, then by looking at how this list of who observed by looking at how this list changes, you can also understand the user preferences of this target user. And finally, we have these risks imposed by external entities, and the most important risk in this case is related to privacy breaches, related to data breaches. So we all know that also very big companies suffered from this data breaches. So here you can see just a few of them, but we know that this is a serious problem. We also know that GDPR somehow is a barrier, makes a company to really consider the security of their data. But again, this is something that can still happen. So this is just a very quick introduction about the problem, just to put the right elements within the overall topic, and then I leave the stage to Yashar who will talk about these learning paradigms and threats in privacy-oriented recommender systems.
Okay, so thank you very much, Tommaso. Can you hear me? So I'm going to share my screen, and please let me know if you can see my screen.
Yes, yeah, sure, we can.
Perfect. Okay, so hello everybody. So in the second part of the tutorial, basically we're going to, together with my colleague Claudio, to talk about learning paradigms and threats within the ecosystem of privacy-oriented recommender system. So in the last slides, it was mentioned which are the actual sensitive data in terms of the user preference data, their logins, and so on, that privacy-preserving machine learning tries to protect. But now we want to see from a technical point of view, from a system-oriented point of view, which are these, let's say, elements. So if you consider a recommender system just like a control engineering system composed of input, output, and the model itself, these are the exact three main elements that we are trying to protect. So input training data, our output labels, which could be the predicted labels in the context of classification or the ranking outcomes, and the model information itself composed of parameter, biases, architecture, and the loss function. And finally, we have the fourth element, which is the other identified information, such as where the data records are coming from. So now let us understand the importance of different learning paradigms and distribution to learn better machine learning models and to protect user privacy. So as we know, standard machine learning models require centralizing the data in a common repository. So for example, let's say we want to train a keyboard prediction model based on user interactions, right? And traditionally, the way we do it is that we create intelligence by collecting all our data on a centralized server, create the model, and then serve it, right? So clients basically all need to talk to the server in order to make predictions, to use the model, and the data is basically stored in the centralized location. So making it extremely easy. The limitation of the centralized approach, however, is that this back and forth communication can hurt the user experience, right? So there could be all those network latencies, there could be connectivity issues, battery lives, and more importantly, there is an issue of data privacy because the data are stored in the centralized location and can be potentially exposed to different types of privacy threats, okay? So you may say one possible idea to address this problem is that each client would store its data locally and train the model on its local data, right? The problem with this approach is that the devices may not have enough data to build a model, right? So what about having a model trained on a server and using or serving the pre-trained model for the clients, right? This seems like a feasible approach to address the previous issues. Well, not quietly, because for example, in the context of a smart keyboard prediction, there may be trendy words that these pre-trained models may not be useful to capture, right? So what can we do to use the advantage of decentralized data and user privacy? And that's where federated learning comes into the picture, okay? So the core idea of federated learning, which is one of the approaches that is discussed in this tutorial, is basically decentralizing learning where the user data is never sent to a centralized server. So how does it work? We start with a model basically trained on the server, distributed to the clients. But since we don't want to, let's say, to annoy the user experience, we will try to identify those clients which are available, so which are plugged in, which are usable, and so on. Okay, and then in the third step, we would find devices that are suitable. And suitable means they have enough data to be used for the federated learning paradigm. So once these data are basically identified, we will deploy the model there, and using their own data, they would update the model, and then they would aggregate, and they would send their model parameters to the centralized server, which is responsible to aggregate the local data. This entire operation in the beginning may not be accurate and needs to be done over several rounds of communication, several iterations, and then gradually you would see changes on your smart keyboard, which is becoming more and more accurate over time. Okay, so this is one of the approaches, one of the promising approaches that is currently being used in the literature of machine learning, and recently in recommender system to protect privacy of user citizens. So to summarize, we can summarize learning paradigm into the following ones. There is a centralized learning, where a centralized server basically is in charge of data collection, data aggregation, and basically clients share their resources directly there. So here you can see that with the arrow, you're showing the flow of the data to the server. Obviously, this approach has a good generalization ability because all the data are stored there, but there are issues with respect to communication and, most importantly, privacy, as summarized here. So basically, these challenges we could summarize as connectivity issues, bandwidth, latency, and connectivity, which is related to the centralized approach. The decentralized learning, which is also known as peer-to-peer architecture, clients share resources or the model parameters directly with each other without the need of a centralized coordinator, right? So this can be seen in this figure. And distributed learning is a centralized approach where the server collects user data and uses those clients as computational loads, okay, in order to exploit their computational resources. Finally, federated learning could be compared with them, where it is an approach proposed by Google in the context of machine learning, and the common examples currently discussed are the user health record data, and basically in the context of smart keyboards, where the core idea is that there is still a centralized server there that makes use of these computational resources of other clients, okay? However, the difference is that the training data now are never sent to the central server, okay? So the user data remains locally, and only model parameters, so like weight, biases, and those things are sent to the central server, which aggregates those information, sends them back to the client to build local better models, okay? So this approach tends to have very good generalization ability. It solves the communication issues because it doesn't need the data to be sent to the central server, and also the privacy of the user are protected because their data are not sender. So at least at some level, the privacy, we could say, is protected because the raw data are not sender. So there are obviously other threats and challenges here, like how you aggregate them and how you can securely aggregate these parameters that would be discussed later on. So to summarize, we would like to point out a few advantages of federated learning, which we have summarized in the following direction. So it comes to data privacy and security. So this is one of the most important advantages that is in line with the goal of this tutorial, that the data pool is not required for the model, and those data remain on user devices, okay? The second one is related to the liability of the model, because in a way, Federated Learning reduces this liability for researchers and so on, because the model basically are trained somehow on local devices. And also that the Federated Learning paradigm can allow heterogeneous data to be used within the framework. The third element is real-time continual learning, where basically this could be seen as another advantage, since we can aggregate the information coming from several devices in a federated learning manner. And finally, we have solved an important issue with regard to the bandwidth and hardware efficiency, since federated learning is still using the computational devices, the computational abilities of nodes, and at the same time, it doesn't require those devices to send their data, saving a lot of bandwidth. So I hope you found this introduction useful. And now I will give the stage to my colleague, Claudia Como, to talk more about attacks and threats within the privacy of recommender system. So thank you very much.
Okay, thank you, Yashar, for this introduction. We're waiting for the slides on the screen. Okay. Okay. Since now we have seen some paradigms for learning, and these kind of paradigms could be affected by some attack. And I try to quickly introduce some of these attack models. But firstly, we can try to categorize this kind of models in 3 different perspectives. Since now we've seen that some of these pipeline of machine learning could be affected by some point of failure during the data training. So we can extract something from the data during the training phase, or we can attack directly the model in order to exploit some drawback, some single point of failure directly into the model in order to extract some sensitive information to reconstruct the model in parallel way with respect to the classical pipeline. But also we can classify this kind of attack in order to understand which kind of knowledge the adversary have with respect to these methods. And in particular, we can classify the adversary with 2 different knowledge. With the white box knowledge, the adversary has a completely knowledge about data or the model or both. And in particular, with this kind of attack, the adversary can try to replicate sensitive information from the data training or to reconstruct the original model. What more, we have also the family of the methods. And in this case, we can classify the attacks between 2 big families. The model extraction, and belonging to this family, we have all the methods that are able to exploit some drawback and some backdoor in the model in order to reconstruct the parameter, the layer of the machine learning model. And we also have the family of encoding information. And in this case, the adversary is able to encode into the data some malicious pieces of information in order to affect the entire pipeline. But we've seen it in detail. From now, we can see that the 4 big categorization of these attack methods. The first one is model extraction attack. And in this case, the adversary can try to extract the information from the model directly in order to train a parallel model to inject some fake output as a machine learning provider, let's say. We also have the feature estimation attack, and in this case, the adversary aims to understand some feature, some sensitive feature from the training set in order to exploit some data about some user or some other kind of sensitive statistical measure about the training set. We also have the attack membership inference, and in this case, we want to understand if some data belonging to the original training set in order to exploit the privacy of the training data. And in the end, we have also the model memorization attack, and in this case, we can use some malicious machine learning provider in order to cheat, let's say, the pipeline and extract time to time some sensitive data from the pipeline and exploit in the end for another malicious way. Now we see in detail some of these attacks. We can start from the model extraction. And in this case, the knowledge that adversary has about this kind of attack is a black box. The system could be affected, are centralized and federated as the learning paradigm point of view. And we can have 4 different methods: shadow training, metamodel, hyperparameter stealing, and reverse engineering. All these attacks belong to the same family, but we can see in detail the shadow training, and in this case, the aim of the adversary is to use a very small query to the original model in order to efficiently compute an approximation of this model. And we use this approximation of model to provide some fake output, for example, or provide some other kind of fake example in the machine learning pipeline. We also have another kind of attack belonging to this model extraction family, and it's the Metamodel Attack. In this case, we learn a separate model that uses the output of the machine learning pipeline and a few query in order to extract the information of the model with the smallest number of query and extract more data information from the target model. From the perspective of feature estimation attack, in this case, we can have 2 different perspectives from the knowledge point of view. We can have a black box attack or white box attack. And also, in this case, the system that is affected by this kind of attack could be centralized or distributed. And we have also, in this case, 4 different methods. Model inversion, also in this case, shadow train, an approach based on generative adversarial network, and power side channel attack. From the model inversion, the aim of the adversary is to learn some statistical properties or some feature about the training set. For instance, if you have a white box attack to the function of our model, we can exploit some information about a patient, for example. And we tend to attempt to reconstruct some sensible data of a patient. This is an example if we have a machine learning pipeline in an hospital scenario. But another interesting kind of attack is the power side channel. And this is affect the CNN belonging to the FPGA-based approach. We use the FPGA to accelerate the training of the CNN, and in this case, we can exploit some backdoor, let's say, of this kind of FPGA to reconstruct the input image that are useful to train our CNN model. Okay, now we have the membership inference attack. In this case, the knowledge of the adversary is a purely black box, and also in this case, the system affected by this attack could be centralized or distributed. Also in this case, we have a shadow training and generative adversarial network approach to attack, but we have also a gradient-based approach and unsupervised binary classification. In particular, we can pay attention to the gradient-based attack, and in this case, the attack is achieved by analyzing the periodic updates that the model captured during the shared training. And the reason that this attack is effective is that the gradients in a neural network are based on feature, and this observation, the participant of the training and the participant gradient and update time to time could be used to infer the feature value that generate this kind of updates. But we also exploit a generative adversarial network to infer some characteristics of the data. And in this case, we use a multitask discriminator, which simultaneously discriminates the category and the client identity in order to understand if some training data belong, if some data belonging to the training data or not. In the end, we have the model memorization attack, and in this case, we can use some approach based on black box or white box knowledge. In this case, the system affected by this kind of attack could be centralized or federated, and we have 4 different methods: encoding, reconstruction, hyperparameter stealing also in this case, and reverse engineering. The most interesting approach is the encoding, and if we imagine to have a white box knowledge about the data and the model, we can use 3 different encoding, sorry. One is Lsb encoding, and in this case, the adversary tried to encode in the training data set some malicious information with less significant bits. We also have a correlated value encoding, and in this case, the adversary can encoding gradually malicious information during the training of the model. And we also have the sign encoding that is similar to the correlated value encoding, but in this case, the adverse use the sign of the model parameter to interpret the kind of attack, in this case, the bit strings. We also could provide some categorization from the point of view of the trust with respect to the aggregator. In this case, the aggregator is a sort of machine learning model, that machine learning provider that capture the information from the user, train a model, and in the output provide some information. The information that put in the output could be a prediction of something, or distribute the model parameter in order to train another kind of another model or another part of the pipeline. In this case, the aggregator is a completely trust about the user or the client that inject the data, but could not trust to release the output of this computation in a sort of plain way. So from this point of view, we can this model could be affected by 2 different kinds of attack: model extraction attack and feature estimation attack. And to provide some defense method, we can use central differential privacy, and with this technique we can try to reduce the exposure of the model to the external environments. So from the point of view of the model, we can use this differential privacy to avoid the model extraction attack, and from the point of view of the data, the differential privacy try to reduce the exposure of the feature estimation attack. But we have also a different perspective in which the aggregator is completely trust about the output, but isn't sure about the the quality of the network or the quality of the user that inject the data. And in this case, the approach that could be affect this kind of scenario could be membership memorization attack. And to avoid this kind of threats, we can use 3 different techniques that we explain in the following of this tutorial: encryption, secure multi-party computation, or local differential privacy in this case, because we move the trust of the aggregator not in the end of the pipeline of the machine learning, but in the very beginning, when the model try to get the data from the user and from the device. And now we can move to the next part, and I leave the stage to Antonio. Thank you.
Okay, thank you, Claudio. Okay, so far we have seen some of the problems that we can have with privacy in recommender systems. And Claudio right now mentioned some of the techniques that we can use when the aggregator, so for example the server to which we provide our data, is not trusted. In this part of the talk we will see some of the most used techniques for privacy-preserving machine learning in general. And in the next part, we will see how these techniques have been applied in the recommendation scenario. So we will start from differential privacy, and we will see some insights about cryptographical techniques. Okay, so the idea is that we want to learn nothing about individuals, but we want to still learn useful information about the population. So I want to learn something about you that are in this room, but I don't want to learn something about a specific individual in this room. So how to analyze the data while preserving the individual privacy? This is a very old problem in literature. And we know that de-identified data are not so secure, and that releasing just statistics is still non-private, and we will see right now why. In the first part, Tommaso showed some of the problems that we had with the de-identified data, so we can surely say that they are not so secure. So you can think, for example, to get an anonymous data set of telephone records and correlate it with the merchant's telephone database. So surely we can obtain some information more about those individuals. Or you can think about Google, that could easily, with its huge amount of information, could easily de-anonymize a database of online purchases. Second, we can see that releasing just statistics is still non-private. So let's think to this example. I can ask, which is the number of faculty members in the university who have heart disease? Okay, and I obtain an answer. Then I ask another query, which is the number of faculty members in the university who have heart disease and are not the president? And I have another answer. But now we know whether the president has heart disease or not, of course, because we can mix the two answers. So we have gained some information. So the question is, what can we learn? Let's suppose that we cannot learn anything about Tommaso. And if I learn that almost all humans have one left foot and one right foot, I am learning something new about him. So in this case, am I compromising Tommaso's privacy? One may think yes, but of course not, because we would have learned the same thing if Tommaso had been replaced by another member of the population. Okay? And so this is the idea behind differential privacy. The outcome of an analysis is essentially equally likely, independent of whether any individual joins or refrain from joining the dataset. So here we see a population and another population without a member. And the idea is that the output of a query or the output of an algorithm should be basically the same. So we cannot learn that that individual or an example of the data was in the dataset. Okay, so formally, we define X and Y as adjacent data sets, where Y is equal to X, but also contains one more example. And we define M, a randomized mechanism, over a data set. So we say that M gives epsilon differential privacy if, for all pairs of data set X and Y, and all possible outcomes of this private mechanism, this relation holds. So we can see this relation, imagine that the ratio of these two probability should be upper bounded by e raised to epsilon. What is the mathematical stuff behind this relation? If epsilon is equal to 0, we have no probability loss, so an attacker cannot distinguish at all the two data sets. So the output of the two mechanisms is always the same given two different data sets. And of course, this will completely burn the accuracy. And the other idea of differential privacy is that once we release the answer, with current and future side information, and also with post-processing, this probability ratio should hold. Okay, let's think about these two examples that is very famous in the differential privacy literature. Let's suppose that I ask you, have you engaged in drug traffic in the past week? And you responded, flip a coin. If tails, then you can respond truthfully. If heads, then you flip a second coin and respond yes if heads and no if tails. This mechanism is known as a randomized response mechanism. So it's just one of the possible randomized mechanism M that we can apply to our data. So in this case, we can just compute all the possible ratio of input and outcomes based on the definition that we showed before, and we can see that this ratio is always 3. This 3 is exactly the value of e raised to epsilon. So epsilon in this case is, of course, the logarithm of 3. And we call epsilon privacy budget because is, of course, the representation of how much you can learn when you ask me something about this population. In differential privacy, 2 or more differentially private mechanisms can be combined, and the composition theorem bounds cumulative privacy loss, so the epsilon, over multiple analyses. So if I ask more questions about the same population, the epsilon of the differentially private mechanisms I am applying before providing the answer sum up. So the combination of k algorithms, each epsilon differentially private, still guarantees k epsilon differential privacy. So in general, the epsilons add up. The good news is that combining more differentially private algorithms, we can carry out complex differentially private analysis. But the drawback is that answering multiple queries, we cannot avoid that the strength of our privacy guarantee will degrade with this repeated use, because we can, of course, converge to the true value. So in this case, epsilon is smaller than k epsilon. So we are figuring out that the smaller the value of epsilon, the strength is the differential privacy. So let's analyze a little bit in practice differential privacy to understand how it works. Let's suppose that the query is how many users in this room have green eyes, and the attacker doesn't know whether the real count is 1000 or 1001. So let's suppose to publish a noisy version of this actual value. So instead of sending the true count, we send the true count plus a Laplacian noise with this constant 1 over epsilon, so proportional to 1 over epsilon scaled. And let's suppose that we publish 1003. Okay, so after applying the noise, we publish 1003. So if we look to the two lines that we have in the graph, of course, the attacker, when receives the value 1003, thinks that it is more likely that the real value is 1001 because, of course, it's more likely because we are more at the right. So we have basically applied this Laplacian noise that has this, this formulation and has this density. From the mathematical point of view, basically differential privacy requires that the ratio between these two densities, so the density of the Laplacian noise applied to the real count and the density of the Laplacian noise applied to another count, so that differs just for one element, is limited between e raised to epsilon and e raised to minus epsilon. Let's think now about this other problem. I ask you how many, let's suppose that I collect some complaints and I want to know how many complaints have been sent. So the attacker has uncertainty about just one user in the dataset and wants to know how many complaints she sent. So let's suppose that we have a user that sent 5 complaints. So in this case, the maximum distance between the real counts could be 5. But if we apply now a noise, the same noise to the real count, we will have the 2 curves at a larger distance. So in this case, we are not preserving epsilon differential privacy, but 5 epsilon differential privacy. Because now, of course, the attacker has more information because a user could move this curve more with respect to the previous example. The take-home message in this case is that we should take into account the maximum contribution of a user. So, in this case, in order to provide epsilon differential privacy, we should apply a Laplace noise scaled by 5 over epsilon. So we are adding a larger noise in this case. Okay, so to wrap up these considerations about the contribution of a user, the idea is that we need to know the maximum contribution of each user of each element. It depends on what we want to protect. So let's suppose that D1 and D2 are 2 adjacent datasets, so the same dataset but 1 element more or with 1 user more. And we define the sensitive delta f of a function f as the maximum distance that we can have computing the same function on the first dataset or on the second dataset. So the idea is that changing one entity in the dataset, the output of the function changes at most by delta f. This does not apply always. We can have something that is unbounded, so the presence of a user, for example, in our dataset could make some unbounded modifications on our output. So in that case, we need, of course, to clamp the values to limit the sensitivity because, of course, then we have to add noise based on this sensitivity. So just to understand better this situation, let's suppose that we want to release the number of users in each age range. So in this case, each user contributes just to one of the statistics that we are releasing. So for example, I am 26 and I will just contribute to the second bar. So in this case, applying Laplace 1 over epsilon noise to each count, we are providing epsilon differential privacy for the released histogram. Let's suppose, on the contrary, that we ask the system how many users, for example, are older than 35, have visited a certain web page and live in the Netherlands. So in this case, I can contribute to more than one statistic. So the sensitivity of my presence in the dataset is 3. And so to make the final answer epsilon differentially private, each answer should be epsilon over 3 differentially private. So we need to release statistics with the same noise but times 3. And the general idea is that the sum of all the epsilon I of all the answers corresponds to the final privacy budget, and later in the hands-on session we will see how this applies, for example, in machine learning. Let's suppose now that we are collecting some answers related, for example, to the favorite color. So in this case, we have an open-ended question. So we have no option, like in the previous case. And if you look at the plots at the left, the second plot completely reveals the presence of a specific individual in the dataset, because we know for sure that in the second plot a user has participated. So applying noise and thresholding to drop rare categories, we reduce the odds of a distinguishing event, because we call this one a distinguishing event. So we can basically try to apply noise to the bar plot at the left, then threshold rare categories, and releasing this new answer, we can reduce the odds that the attacker knows that that user participated to this question. And we see, of course, that the higher the threshold, the lower is the probability of a distinguishing event, of course. Okay, so given that, we end up with this new definition, that is the definition of epsilon delta differential privacy, in which we create the same definition as before, but we add this value delta here. This delta captures the odds that something goes wrong. So basically that we are in the situation that, for example, the threshold is not enough to hide a specific user. But this delta actually is a cryptographically small probability, smaller than the chance of an asteroid flying into the Earth. It's basically the probability of a disaster. So it should be a very little value. Okay, just to understand better what mathematical we are doing here, we can see that when we apply some noise to the data by means of this mechanism, and we consider the ratio of the two probabilities, we are basically creating a new random variable that is the privacy loss. So given the output, the attacker can, of course, increase his knowledge, or decrease his knowledge, or not changing the knowledge. So let's suppose that we release 1003 in the example that I made before. If I release that that value, and the real count is, for example, 1000, in that case, I am increasing the knowledge of the attacker. And on the contrary, if I release a value that is far from the real value, we are decreasing the knowledge of the attacker. So far, we have applied Laplacian noise, but let's think about applying Gaussian noise because we like the Gaussian distribution. In this case, what happens? The cumulative probability and related with the exponential of this privacy loss gives us this plot. So we have a part of this plot in which we can see that there is a little probability for the loss to go above this epsilon threshold that we fixed before. And that's basically the terrible event that we are mentioning before. But since we have to measure this terrible event, we can consider the area over that threshold, and that exactly represent the parameter delta that we were mentioning before. Okay, so the question now is, so with Laplacian noise, we didn't have problems like this terrible event. Now with the Gaussian noise, we have the possibility, the remote possibility of a terrible event, but we still have this possibility. So why apply Gaussian noise? Let's suppose that we want to release the number of users that bought each book in a vector of, so we have a catalog of 1,000 books in a vector of 1,000 element. And we want to protect the presence of a user in this dataset. And this is something that can apply to recommender systems, of course. In this case, if we want to protect all the count, based on what we said before, we should apply 1,000 over epsilon Laplacian noise, okay, to each element of the vector. So that happens because the sensitivity of this function producing this vector is 1,000, because if I am in the dataset, I can modify the dataset by 1,000 elements. And so far, to measure this sensitivity, we use the Manhattan distance. So we just measure the absolute value of the differences. The good news is that the Gaussian noise needs to be scaled by the Euclidean distance. So we use the L2 sensitivity. So in this case, we can apply a very smaller noise to have the same privacy effects. That's because the L2 sensitivity grows much more slowly than the L1 sensitivity. It depends actually on the number of statistics that we are releasing. But with big vectors, of course, Gaussian noise could be the best solution, or better than the Laplacian noise. Okay. After the Laplacian noise and the Gaussian noise, we should consider also the exponential mechanism. This mechanism is important because sometimes we have queries whose answers are categorical, or are some real numbers, but we cannot change at all their value. We have to release just one of their values, or are returned by functions with very high sensitivity. The idea behind the exponential mechanism is that it selects the best element in terms of a certain utility, and to do that, we should define an utility for each of the possible answers, and in that case, we should output the element of our range of possible answers with a probability proportional to this exponential here. And this mechanism is proven to guarantee epsilon differential privacy. So I will go to an example right now. let's suppose that we want to pick a good day. This is something that, a kind of table that we usually build with our colleagues, for example. And each of the people involved has to check the availability on certain days of the week. So what we usually do is for each day, count the number of available people on that day and return the maximum argument of this vector. So in this case, we have no privacy at all. An alternative is to apply differential privacy to the count. Okay, so we can, for example, use the Laplacian or Gaussian mechanism to, as we have seen before. But, and this applies better for this situation, we can use the exponential mechanism. So, in this case, we have counted how many people is available on each day, and we have to release as categorical values one of those days. So in this case, we have, of course, a higher utility for Wednesday based on the based on a utility function that we have to define, and then we can release one of these days based on this probability here. Okay, so in this case, we are going to release, of course, a categorical answer, because we will respond with one of the names of the week. And with the higher probability, we will release the answer Wednesday. But it can happen that we release also another day of the week. So, given all these stuff, what about differential privacy in machine learning? Usually, just adding noise to the output does not work, because we use usually non-convex functions that are very, very, very sensitive, and we will need too much noise. And it is usually also hard to characterize the exact dependence of the final parameters on the data. So, in that case, it could be also hard and tricky to understand which is the sensitivity. So the idea that usually applies is to take the standard algorithm and add appropriate noise during the training. And later in the hands-on session, we will see some example with the matrix factorization in recommender system, of course. We have here to make a very simple distinction between central differential privacy and local differential privacy, because in the first case, we trust the aggregator and we send to it all our data, and in this case, we can obtain, of course, a higher accuracy, and the final output is protected by means of differential privacy. And this is the case of the US census, where they released these census data with differential privacy. On the right side of this slide, we see local differential privacy, where the users do not trust the aggregator, and in that case, they should apply the differentially private mechanism before sending the data. And in this case, we would obtain, of course, we will need, of course, a higher noise. And this is the case of some currently used mechanism that are Google wrapper for Google and for Apple emojis that collect, for example, our usage about emojis with differential privacy. So they count the emojis we use with differential privacy. So in short, differential privacy guarantees strong privacy. We no longer need to model the attacks. We have a privacy loss that is quantifiable, mechanisms that are composable and still quantifiable, and it's useful for analyzing any algorithm, also the toy example of the randomized response about the drug traffic. To conclude, we see these two other mechanisms. They relate to the cryptographical world. And we start with secure multi-party computation, in which we want to compute a function jointly while keeping our input secret. So we want to compute the result of this function f, and we have each one private data. We want to compute the same result together, but without revealing each other or to another party the input values. Let's suppose, for example, that some co-workers want to compute their average salary without revealing each other their individual salaries. So which are the insights of this secure multi-party computation? The computation is distributed across multiple parties with no one seeing the other party's data. We can perform both training and inference on encrypted data. So there is a kind of homomorphism in this case. But the drawback is that it generates computational and communication overhead, especially communication overhead. Okay, let's consider this example just to understand how it works. This is the additive secret sharing. It's the simplest secure multi-party computation scheme in which we distribute random pieces of a secret among some parties. So 3 friends have drunk some beers and they don't want to reveal each other how many beers they drank. But they still want to compute the average of the beers they drank. So Alice drank 10 beers, Bob 20 beers, Caroline 30 beers. And they distribute these values. So for example, let's consider Bob 20 beers in this way. Bob splits the value in -8, and he gives this value to Alice, 10, and he keeps for himself this value, and 18 to Caroline. Okay, so we call all these horizontal values, let's say, shares. They are called shares of a secret because we are sharing just a little piece of information to other parties. And if we if we perform the operation of sum, in this case, because we want to compute the average by the columns, we obtain some values, -3, 48, and 15, which are still not meaningful values. But when they sum these shares, their average is 20 beers, which is the real average. What happened is that the sum of the shares that we see at the bottom is a share of the sum. Okay, so for example, in the second column, 3 plus 10 plus 35 is 48, and 48 is a share of the sum of 10, 20, 30. Okay, so we have basically split the result of the computation without revealing the initial values. These were the additive secret sharing scheme. That is the simplest one, but we have also some other schemes. You have to consider that in the previous in this scheme, when one party drops out, we cannot compute the average. So, for example, if Caroline drops out, we cannot know the result of the computation. So there are other possible solution. For example, we have this polynomial solution in which we build a polynomial of degree r, and r is the minimum number of parties that should keep alive to reconstruct the secret. And then we have this SPDZ protocol that uses the additive scheme for the linear operations, but also introduces the multiplication between the shares. And to do that, we need a honest crypto provider that shifts the computation in an online pre-processing phase. And this, of course, you can imagine, introduces a lot of communication overhead. These schemes are adequate for integers, and if we want to use them in machine learning, we should also introduce the fixed precision encoding for these shares. The last thing that we see in this part is just one slide about homomorphic encryption, and it is used to allow meaningful calculations on encrypted data in situations in which secure multi-party computation, for example, does not apply. First of all, we need just one party to encrypt and decrypt our data. So we send our encrypted data, and we don't need other parties to decrypt them. We can perform operation directly on encrypted data without interaction with other parties. And the result is equivalent to performing analogous operations without the encryption. And that is the homomorphism. The drawback is that it is computational expensive and that it allows a little set of calculations. So from a mathematical point of view, we have that an operation applied to two encrypted values should be an operation applied to two encrypted value should be equal to the encrypted value of the same operation applied to the encrypted values. And we have three categories of homomorphic encryption: partially, somewhat homomorphic encryption, and fully homomorphic encryption. They are increasingly computational expensive, but they allow more operation on the data. So to conclude, the final trade-off is that when we want to develop private machine learning, we need to do an artful balance of efficiency, accuracy, and privacy. So homomorphic encryption and secure multi-party computation are often replaceable. With homomorphic encryption, we have little interaction but expensive computation, and with secure multi-party computation, the computation is cheaper, but we need a significant amount of interaction. Instead, differential privacy replaces accuracy with efficiency, because we saw that with the cryptographical schemes, we didn't lose accuracy. Instead, differential privacy replaces accuracy with efficiency, and if the coordinator is trust, we can send it plain data to preserve more accuracy. So this travel with these techniques as ended here, and I think that now we have the time for a break. And we will see at 11:30. Okay. Okay. We can answer now or later. It's quite. Okay. Yeah. Okay. Thank you. Okay, to the remote audience, we will answer to the question when we come back from the coffee break. Thank you.
Okay, let's start with the second part of this tutorial. We will answer the questions before the hands-on session. So this is this part that is about the trending research presented by me and Walter. So we selected, in our opinion, the most relevant works between 2018 and 2021 in different domains, point of interest recommendation, fitness trackers, news recommendation, movies, web browsing, and online shopping. The first work has been published this year, 2021. The domain is the point of interest recommendation. That is the most common domain in privacy-preserving work. The adopted paradigm is collaborative filtering, and it has been published on IEEE Access Journal. So what is the problem? The problem is that it is estimated that only 4 locations are enough for identify most people. The task of POI recommendations is that given a user with a check-in history, at a time t, we want to recommend a set of interesting point of interest at time t+1. The solution proposed in this work is based on local differential privacy, before explained by Antonio. So what is the main difference? Just a brief recap. Differential privacy needs a data curator. Local differential privacy, in local differential privacy, each user perturbs her own data. So we don't need the privacy data curator. So the original data never leaves the user device. That is a very big advantage of this technique. This is the model proposed by the authors that is named Spiral. So we have the check-in history for a given user. So he moved from P1 to P2, from P2 to P3, and so on. These are the transition patterns of the user. So the user samples one pattern, he perturbs it, and he sends it to the central server that will aggregate all the received data. The evaluation has been carried out on 4 state-of-the-art datasets: Gowalla, Taxi, Yelp, and Foursquare. The metrics adopted are hit ratio and MRR. And in the results, the authors demonstrated that Spiral is better than several POI recommendation algorithms, and is able to really preserve the user privacy. The second work, also this work has been published this year, again on POI recommendation. The paradigm is again collaborative filtering. The journal is user modeling and user adaptive interaction. In this work, we have a twofold contribution. The first is in terms of accuracy. Indeed, the authors propose this additive Markov chain that, with respect to the first order Markov chain, is able to exploit the whole check-in history of the user, instead of only the latest one as the first order Markov chain. The second contribution is in terms of privacy preserving. So we have this relaxed differential privacy that Antonio explained before, that has two parameters, the epsilon, that is well-known parameter about the privacy budget, and delta, that is the maximum probability to have a breach of privacy. So what is the goal of the model? Is to find the right trade-off between the two parameters, delta and epsilon. This is the model. We have the check-in dataset for a user. The probabilistic differential privacy module receives the aggregate statistics from the dataset and receives also the aggregate queries from the location recommender system. And it answers with noisy aggregate statistics. Now, the location recommender is able, by exploiting the noisy aggregate statistics, to generate the recommendations. The evaluation, in this case, has been carried out on these three state-of-the-art datasets, Foursquare, Gowalla, and BrightKite. The metrics, in this case, are the accuracy and the efficiency in terms of running time. And also in this case, results show that the model has a very high recommendation efficiency and accuracy and a strict location privacy. This work has been published in 2020. The domain is related to the fitness trackers. The journal is user modeling and user-adapted interaction. This work is really interesting because the outcomes can be exploited also in domains different from the original one, that is the fitness tracker domain. So, what is the goal of this work, of this investigation, is to support the users in defining their privacy settings. The idea is to exploit this personal data manager that is a sort of hub between the user data, the third parties applications, and other service providers that ask for the user data. So the contribution is related to a formal definition of the user privacy preferences, the definition of a set of privacy profiles for the user, and the prediction of the user preferences in terms of privacy. This is the model. So we have here the user devices, the dedicated third parties applications, and the most interesting part of this model is the IoT ontology. Indeed, the authors define this ontology in order to bridge the gap between the IoT vocabulary and the privacy vocabulary. In addition, this ontology also addresses the GDPR requirements. This is the result about some questionnaires that the authors administered to the users in experimental evaluation. We can see that the settings are grouped in three classes. A, that is application settings. So the the settings related to the device application. S is the smartphone settings, and G is the GDPR settings. We can see that the users are willing to disclose demographics related, for example, to the gender, to the age, with a high percentage of disclosing. Related to the smartphone settings, the users release data related to the location, the Bluetooth, the mobile data. And in terms of purposes for which the user are willing to release their information, we can see that in the first places of this ranking, we can see the health and safety purposes. This is the first method that the authors propose for privacy settings, that is the smart settings. In this case, the settings are related to the average tendency of the people. So we have these settings coming from the centroid vector of the difference preferences of the different users. This is the second method that is based on the idea of privacy subprofiles. Here we have two subprofiles. The first one is minimal. The second one is unconcerned. And we can see that for each profile, we have different settings associated. The third method is based on a set of questions to the user. So we have, would you share your photos? Yes, no. Would you share your first name? Yes, no, and so on. And these answers are then transformed in privacy settings. These are the results in terms of accuracy of the different methods for acquiring the preference settings. And we can see that the most accurate one is the peak profile method. So with the subprofiles that we saw before, followed by the direct prediction, indirect prediction, and smart method. So, a very interesting outcome from this work is that users care more about who will receive their data rather than what. So, in the privacy setting, the service provider plays a very crucial role in the user decision. This work is about movies and in the domain of movies, recommendation, and web browsing. It has been published in 2020 on the journal Expert Systems with Application. Here we can see that there is the traditional problem related to the privacy concern, and there is this other problem that is related to the partial view of the data. Indeed, the authors state that one of the problems is that the third party's application can access only to the data released for their own application. So they also criticize the two most used approaches that are perturbation, because in their opinion, the perturbation generates lower quality recommendations. And the second approach, that is the cryptography, in their opinion, has a very high cost in terms of communication and computational effort. So the solution is to define this novel architecture for a recommender system based on Open PDS, Open Personal Data Store. This is the Open PDS architecture. Here there are the user data. So there are the third-party applications that asks for a computation. In this case, the answer is generated by the safe answer module. We have a safe answer module for each application. So the safe answer module is the only module able to access to the user data, and it answers only with the result of the computation. So the user data remains on the user device. So the proposed idea is to propose this recommendation algorithm based on OpenPDS, and to shift from a collaborative filtering approach to a content-based one. And the other idea is to allow service providers to access also to data that are not generated for their specific application. This is the model, so we have the user, we have the data produced for different service providers, S1, SP, and the recommendations are generated by exploiting all these data. The evaluation has been carried out on the movies and web browsing domain, and the authors compared the performance with popular non-privacy aware collaborative filtering algorithms, and they showed that their method is comparable with classical collaborative filtering algorithms and improves the performance thanks to the capability of the system to access to data provided by other service providers. This is another work that is related to the news recommendation domain, published in 2020. In this case, we have collaborative filtering with federated learning. So, what is the motivation of this work? The authors declares that disclosing the user behaviors related to news website may bring catastrophic consequences. I don't know if this is really true, but we trust them. So the solution is the proposal of a privacy-preserving method that is based on federated learning. So also in this case, the data never leaves the user device. This is the model, so we have the news model and the user model on the user device. So we have a local differential privacy module for improving the privacy preservation, the privacy protection. There is also a clipping step for avoiding the gradient explosion, and then a randomized gradient is sent to the central server for the aggregation and for building a new news and user model. The evaluation has been carried out on Dressa and Microsoft News, and in this case, the authors demonstrated that this method can achieve performance comparable with other state-of-the-art news recommendations, for example, based on factorization machines. So the next part is by Walter.
Good morning. I will focus on another bunch of papers, and in particular, I'll focus on matrix factorization. Obviously, matrix factorization is a recommendation technique that is well known, so I'll try to summarize it in a couple of sentences. We can decompose the user item ratings matrix, or a binary matrix, into two different matrices for user embeddings and item embeddings. An item embedding multiplied by a user embedding let us obtain a certain value of the rating. And this technique is also used, obviously, to fulfill a sparse matrix that we have at the beginning. So, since this is a very important technique, there are a lot of papers that focused on that. And what we want to do is to have an overview of them. Since we are quite late, I'll try to be as fast as possible describing them. For each of these papers, as Lucio did, we have an introductory scheme, and then we will have like a spoiler. And this was created for you in the slides, just to recap what we are discussing today. So the first paper is this privacy-preserving point of interest recommendation using decentralized matrix factorization, proposed at EEI in 2018. And here the core ideas are related to the communication within the framework and we will see that we will use an idea of nearby users, and how far this communication should hold, and what is the amount of the information that we should send through this network. So the first aspect that they analyzed was related to the characteristics of the dataset. So they analyzed Foursquare and Alipay, and they ordered the user IDs and the item IDs, and they discovered, and you can see here, that basically we have different clusters of interactions. And these clusters are mainly related to cities, obviously. So they thought, if this is the situation, why we should keep these very, very big matrices instead of creating much smaller datasets and matrices to use. So this is the first idea, and to realize it in an efficient way, they compute the adjacency matrix and matrices to elaborate if a user could be a neighbor of another user. So based on that, we come to the second question. If we have this situation and we can connect each user to another one, how far this communication should continue? And here comes the problems, because if we maintain a long communication, so we go very far, we explore the network, we will obtain more reliable results, but also all these communication and computation as a cost. So the idea was to be inspired by the random walk theory, and they were also inspired by the Markov decision processes, and they computed transition probabilities to explore the first hop of exploration or the second hop of exploration in this network. And based on that, they realized these paths, these walks in the network. But the second question remains, what kind of information should I share? Because I want to keep everything private. So they decomposed the embedding, the item latent factor, in an additive way. And they obtained a global latent factor P and a personal local, let's say, latent factor Q. And here the idea is that we can update as usual on our model, making our gradients and everything, but then we can use our personal variant, our personal gradient of the global one, and we can send this less important information to the network. So we keep the gradient of the personal item factor, and we send the gradient of the global item factor. And this is very important. Please remember the fact that they are sending this gradient along the network. The second paper is titled Metametric Factorization for Federated Learning Predictions. Sorry if I'm going so fast, but I'm trying to save time for the hands-on session. And it was presented at CIR in 2020. And here the spoilers are that they use a collaborative memory, a meta recommender, and a rise dimensional generation matrix. And now we will see what it means. First of all, we can have an overview of the whole framework. In the left-hand side of the framework, you can see on the left the collaborative memory, let's say a shared memory. Then on the right-hand side of the left picture, you can see the meta recommender, and both of them are are stored on the server. And on the right-hand part, you can see what is on the one's device. So this prediction module. This collaborative memory basically is based on a matrix that is called M here. And it is a shared matrix that multiplied by the user embedding creates another vector that is called collaborative vector, this CU. And we will see that this CU is used to feed the meta recommender. For the upper part, we can see that the original item latent factor matrix has been decomposed in two different matrices. The first one is low dimensional, and that's the idea to save computation. Okay, this low dimensional item embedding matrix ILU, and the other one is another matrix that is used to retransform this low dimensional matrix into the original item latent factor matrix. And both these matrices are trained using a multi-layer perceptron, since all of us and all the reviewers love neural networks. The final part is the prediction module. And here we can recompose the item latent factor matrix, and we can combine it with the private user embedding. And again, we have a neural network as a prediction module, and then we obtain the ratings. Now we can move to a milestone that is titled Secure Federated Matrix Factorization. And this is a really, really important paper. And it was presented, let's say, accepted at IEEE Intelligent Systems in 2020. And it is based on two very important ideas. Let's start with the second one. They use homomorphic encryption, and we have seen what does it mean. But also, they discover that sending the gradients does not preserve privacy. And this is the reason why I told you to remember the fact that we were sending these gradients along the network. Because all the papers before this one thought that, okay, I don't want to share my ratings, I can share my gradients. Come on, it's okay. No, it's not. And they were able to derive these two equations. And here you can see that we have G that are the gradient at a certain time, a certain iteration T, and in the subsequent iteration T plus 1. And then we have alpha, beta, and gamma. And also, and that's all I think there. Okay, and if you think about it, if the gradients are public and alpha, beta, and gamma are composed using item latent factors that are public and the gradients, we can obtain the user embedding. And with the second equation, you can see that if we have that, we have the item factors V, then we can compute the ratings. So basically, they were able to prove that, okay, this is just the last part of the proof, obviously, but they were able to prove that sending the gradients is not safe. And this is really a thing that changed the world in matrix factorization, in secure, let's say, matrix factorization. So they decided to move to an encrypted model. So they used this technique of homomorphic encryption that we have seen before. And basically, the different steps that the server follow are these. Obviously, I'm summarizing them, but I tried to keep on the slides for you later the most important information so that you can recall them by reading now. So the first thing is that obviously the server starts by encrypting the item factor matrix, and it makes it available for all the users to download. All the users are able to download it, and they decrypt it, use it to update their model, then they take the gradient and encrypt the gradient. And then they send it back to the server, and the story starts again. So basically, they, for the first time, they were able to ensure that even though we have a man in the middle or whatever attack, if we use a homomorphic encryption, then we will be able to send these gradients along the network. And obviously, since they are using an encryption method, we don't have a decrease in performance because we encrypt, decrypt, and use the same data. So we can move to the next one, novel collaborative filtering recommender friendly to privacy protection. It was presented at IJCAI in 2019. Here, the ideas are related to the usage and of a pre-trained model. Then they try to modify it a little bit using homomorphic encryption, and then they try to find some solution for the problems that occur. So the first method that they use is to pre-compute the model, pre-train the model, and then they follow this procedure. The client encrypts the rating vector, send it to the server. The server uses this homomorphic operation to create encrypted predictions and send the encrypted predictions to the client. Now the client is able to decrypt them and use them. That's okay, but we were not able to train the model. So the next step is to say, okay, we can use a pre-trained model, but now we can try to fine-tune the model. So what we do is the client encrypts not only the rating vector, but also an indication vector with ones and zero for a binary, let's say, interaction vector. And the server now can use these encrypted vectors to update the model, not just to create the predictions. So since we are in homomorphic encryption, what happens is that when they update the model with encrypted data, they are encrypting the model. So now we have an encrypted model. Then, okay, the predictions are sent back to the client, and the client can decrypt them and use them. But now the problem is that all these ciphertext-only operations are very, very expensive. And even though we want to perform a small number of operations, that could be a problem in a real system. So they found this solution. They try to sparsify and quantize all the metrics that are involved in this computation. So they sparsify the model that they have at the beginning, and they remove all the parameters that have a little impact on the results, and they remove all the weights that have values below a certain threshold, and then they quantize the weights. And in particular, they use 512 clusters. In this way, they obtain another side positive effect, that is that more than one weight has the same value. So maybe they can reuse the computation, the multiplication that they did. And so this was their solution in this sense. Now we can move to differentially private matrix factorization, and this is a quite old paper in IJCAI in 2015. And we have chosen this paper because they analyzed two different scenarios, and this is very important. They analyzed the scenario in which the recommendation system could be considered as trusted. Okay, so we can trust the recommender and we can send some information to it. But they also analyze another scenario in which we cannot trust the recommendation system. So in the first case, obviously, the goal is always to preserve the epsilon differential privacy. But we will see what happens if we do it in the two scenarios. And in particular, the goal is to keep the matrix of user embeddings private. they find a solution that is to perturb with a noise, of course, as we have seen before, the objective function. But if you think of it, we never send the user embedding matrix along the network. What we send is the item embedding matrix. So their idea is to fix the user embedding matrix. They compute, they update it, and then they fix the user embedding matrix, and they transform only the item embedding matrix into a variable, and they perform they compute the gradients there. Okay, they perform the training. And this is their idea. Okay, so we can compute and then fix the user embedding matrix, then we move to the other matrix, we fix it, and we add the loss, and we compute the gradients. And then these perturbed gradients can be sent. Now we can move to the scenario in which we have to face an untrusted recommender system. And this is more similar. I recall you that we are in 2015, and this is more similar to what we have seen with differential privacy. Obviously, they told us that they could use these secure multi-party computing methods and cryptographic techniques, but as we have seen before, using these kind of techniques is very time-consuming and in general is too costly. So what the other question is, okay, but we have already perturbed the loss. So why we are talking about that? The fact is that the untrusted recommender system could be able to obtain the item latent factors and the gradients. But how? Obviously, if we think of it, in the 2015, they understood, but not proved, that iteration after iteration, all this modification that we do, all this noise, will be eliminated. And an untrusted recommender system will be able to reconstruct the gradients and everything. So they decided to do what? To add an additional noise done by the users, as we have seen in differential privacy. Years before, that was applied to recommender systems. Then we can move to this JODPMF, Differential Private Matrix Factorization Learning through Joint Optimization, accepted at Information Sciences in 2018. And here the idea is not that a big idea, because we have seen that before, but again we have to remember that here we are in 2018, they use differential privacy with Laplace noise in the objective function. So like a mix of the two that we have seen before. And they use another idea of correlating, K-correlating metrics that we will see. So they carefully design a Laplace noise factor, and they applied it to the objective function. But here in this paper, the interesting part is that they formalize everything, and then they prove that this optimization problem constrained by the perturbed objective function still satisfy the Epsilon differential privacy. And that is very important. Not a lot of papers do that. And finally, they introduced this other idea that is an old idea, but they used it together along with the differential privacy. That is these co-rating equivalent users. What they are? If we can imagine a binary interaction vector of a user with ones for the interaction and 0 for not interaction, we can say that two different users, if they have this vector that is equal, they are considered as co-rated equivalent users. And so a rating matrix M that satisfied the K co-rated privacy if every user has at least K minus 1 co-rated equivalent users, as we have seen before. So to do that, to apply that, obviously, what do they need it? First, they needed to split users into different groups because it makes no sense to try to compute it in the old dataset. And then, obviously, they needed to transform some of the null elements, so the zeros, into ones. And to do that, okay, to increase the number of privacy equivalent users. But to do that, they needed a notion of similarity. So they based on a previous work by Zhang in 2014 that tested 4 different methods to fill this data. And they found that trust derivation and Pearson correlation similarity were the best method. And in this paper, they decided to use trust derivation. And finally, we have this differentially private graph link analysis based social recommendation. Also in this case, it was accepted at Information Sciences in 2018. And here, the most important idea of this paper is that they apply differential privacy to a novel domain, the social recommendation. But why is that important? Because in 2011, Makanava-Yala told that it was not possible. Because it told that modifying an arbitrary social link should have a negligible effect. Otherwise, obviously, we would have a big effect on the final recommendation. And what does it mean, having a big effect? It means that we should have a high value of the sensitivity of the single modification. So he made this analysis, studying the sensitivity, and then saying, okay, the amount of noise that we should introduce will be too big with respect to the pure performance that we will obtain. But here, the authors propose another thing. They say, okay, we can recall what Antonio told in section 3, that the sensitivity captures the maximum extent of the output of a function that could be affected by any single input. So, Makanava-Yala analyzed the recommendation function, the utility function and the recommendation function, and obtained a utility vector. Obviously, we are if you implement recommender systems, you always obtain them. But the problem was related to the fact that Makanava-Yala summed these, the values of these utility vector. So they complained about that, and they questioned that, because they considered that Makanava-Yala computed the maximum sum of this affection, and they greatly overestimate the sensitivity value. So they redefined the sensitivity based not on this utility vector, but on the single values, and then rederived the values of epsilon that were needed in their case. And they opened a new world for graphs again. And I try to be as fast as possible and to give you the right intuitions about those papers. And I think that now we can connect, or better, we can see what this night for us, but yesterday for San Francisco, Twitter team member Luca Belli told us about privacy at Twitter. So if it is possible, yeah.
Good morning, everyone. I am Luca. I work at Twitter, and today I am going to talk to you a little bit about the case of Twitter. First of all, let me introduce myself. I am a staff machine learning researcher at the Machine Learning Ethics, Transparency, and Accountability team here at Twitter that I co-founded 3 years ago. After getting my PhD in Italy, I moved to Boston for 3 winters, and then I had enough of the cold winters, so I decided to move to sunny California. And so this is what I was expecting to find, and this is what I actually found. So I'm currently in San Francisco, and that's why you are getting a video recording of me today. So today we're going to talk about important problem, which is obviously privacy in recommender system. Although I would like maybe to try to reframe the problem a little bit in terms of how we can better respect users' choices. And we are going to see a couple of examples of that, practical examples. So maybe let me start by saying that I think, Twitter case is a little different in the sense that, Twitter data is mostly public. There are obviously exceptions. There are private users who are not public. And even for public users, there are certain data that are private. For example, how many DMs you received or sent, or how many impressions any of your tweet had. Of course, you as an author can access this information, but no one else, a part of you can. And so for public user, every kind of engagement on the platform is public. Everything they post is public. Everything that they like is public. So in some sense, that also simplifies the problem here. Plus, if you ever register for a Twitter account, you might have noticed that we don't really ask too many questions to our users. We don't really ask a lot of data to the users. Historically, there's been sort of this tension between asking for more data because that's a way for a recommender system to provide better recommendation. But at the same time, there are certain kinds of data that we might not want to collect and use for recommendation at all. And we'll see maybe later when I'm going to talk about the fairness, how we can sort of resolve this tension. So what does this concretely mean in the case of Twitter to respect user choices? Well, let's look at an example. So, when you post a tweet, you are in control of that in the sense that at any time you decide to delete the tweet. And I would expect as a user that the deleted content is not part of the training data for neural models. And so how can we solve this problem? Well, there are two solutions we can think of, and as in many cases, a combination of both probably works best. The first one is to train often models using fresh data. What does it mean? So if I regularly retrain my model using the latest snapshot of data, I can guarantee that the data that I'm training on is the most the newest version. Therefore, anything that's been deleted since last time that models were trained has been scrubbed away. At the same time, there are certain production models that are really huge, and they might take, days, order of days to train. And this is not maybe it's a very costly process, but from engineering perspective and just a time perspective. And so another technique we can use here is try to break down this one big model into multiple smaller models. For example, embeddings. For example, let's assume you want to use the content of a tweet as input to your model. So you could put the entire sort of all tweet feature in your model, which will probably make the input space huge. Or you could use a pre-train, let's say some sort of like tweet-to-vec model as an input to the other model. In that way, both parts are smaller, more manageable, and it's easier to retrain them and to make sure each of them is sort of fresh. In fact, we had a paper a few years ago at a KDD workshop in London on how we use embedding at Twitter. Another sort of tenet, classical tenet of a recommender system is how we want to how we want to infer user preference by their explicit behavior. So the idea being, a user has some sort of preferences in their mind, and the way they operate on the real world, for example, by engaging with content, reflects these preferences. And so we can reverse engineer this project by looking at their behavior and then figuring out what they're actually interested in, and then recommending content that's that they might like. This is how the classical collaborative filtering works, right? So we'll have this huge item times user matrix. We try to factor that, and then the latent variables or the latent dimension, the latent space is going to represent the interest space for the users. And then we can see how items that a user engage with, how similar user engage with items and suggest those. But again, this is a very sort of trying to reverse engineering a process, and also this latent dimension do not necessarily represent sort of human understandable, right, real world concepts, right? These are just, again, random, sort of not random, but like giving a dimensionality reduction technique, we just take this dimension to be the topics. And so what if we can ask the users, excuse me, we can ask directly the users what they're interested in, and most importantly, what they're not interested in directly. And so this is exactly what Topics is trying to do for Twitter. So if you're not familiar, Topics is a new product that Twitter has. So on your timeline, instead of following specific people, as you would usually do, you can decide to follow a topic. There are certain topics that's being pre-created for you. So for example, you can say you like dogs and coffee, or travel, or photography, any number of things. In that way, we are not trying to infer user preferences. We are respecting their choice in what they tell us directly that they're interested in. And there's also stories of how people might not want to engage with certain kind of content to make sure they're not skewing the recommender system for the future. So for example, I know I do it sometimes when I'm listening to music, and maybe there is one song that is maybe different from what I usually listen to. And sometimes I'm afraid of listening to that song because that might skew my Twitter experience. So in that way, again, there is nothing that is, the preferences are stated very explicitly by the users. And so maybe if I can give another concrete example of what we did, and this is also very relevant for this conference because it's part of RecSys conference as well. So as you might know, every year the RecSys conference partners with someone with an industry partner to find a problem that is both interesting as a research problem and it has concrete application. So for 2020, 2021, Twitter partnered with the RecSys Challenge to sort of try to answer the following question, which is, given a reader, so a user, and a tweet, what is the probability that that reader would engage with that tweet? As you might know, Twitter is as an algorithmic created timeline. So the tweet you see are, or can, that's you can also have reverse chronological order, but the tweets can come algorithmically ranked. So this problem is very relevant for us, although it's also a very interesting area of research. And so how do we make sure that user preferences I discussed before were actually ported in this challenge? Well, something interesting is that our data set was actually being kept constantly in sync with the Twitter platform. So let's assume my tweets were in this data set. If I deleted a tweet on Twitter, also the same deletion will show up in the data set. So that's sort of like, it is a shrinking data set, which is kind of like a interesting and maybe novel approach. But in that way, we made sure that if a user wanted their content deleted, that would be also deleted in the data set. There is also another thing that I'd like to talk about that we did for the RecSys challenge, which is we also added fairness constraints. So, you know, historically, people might try to optimize for a single metric, for example, accuracy. But what we tried to do in this case was to also make sure that the quality of recommendation was independent of the popularity of users. What could happen is that more popular users tend to produce more content, and therefore, when train a system, that system might skew more on the popular user, therefore providing a better recommendation for users that are already popular. And so we said that we wanted quality of recommendation to be independent of the popularity of the author of the tweet. I don't want to go into many details here. I will invite you to come Friday to the RecSys Challenge workshop to learn more about that. But the reason why I'm talking about this, because I think that is, you know, the perfect introduction to what I think it's the next frontier and the next important thing in RecSys, which is what is called FACT. That stands for fairness, accountability, and transparency. And, you know, this is an umbrella term that describes a lot of open research problems. I also want to, you know, this is one of the community that has been thinking about this kind of problem for the longest time, even though now sort of fact in machine learning is getting more and more important. The RecSys community has been thinking things about like diversity of recommendation for a long time. We had a FlatRec workshop last Saturday at this conference as well. Although I would also say that there are still a lot of open questions in this respect. So one being, you know, what does it even mean for a recommender system to be fair? You know, fairness is not a mathematical concept per se. This is mostly a societal norm. And so how do we apply that? Especially when different parts of society might interpret fairness in different ways. How can a global company like Twitter, for example, sort of try to embrace all of these things? Honestly, I think that is one of the area where all the new techniques we're learning about today, for example, differential privacy, homomorphic encryption, client-side computation might really make a difference here. Because I was saying earlier, there's always this trade-off between, you know, getting more data from our users versus the quality of recommendation. Well, what if there's a way of making sure that the recommender system are being fair towards different groups without actually getting the data? And so you could think, you know, you could see a future where all this data just lives on the client side, on the user side, and never leaves their phone or, you know, their sort of devices. In that way, there is no centralized repository for all these all the sensitive data. So I'm really excited to see what the future will hold for this kind of thing. And the other, I think another interesting problem here is like, you know, in a world where all this, the final recommendation is not given just by one model, but a chain of multiple models that are all maybe black box models, so they're all very difficult, if not impossible to interpret. How can we give a useful context to the final user? Like, we are recommending this item because of this reason. How can we improve on that? So as I was saying, these are still very concrete and active area of research. And I believe that, you know, it is very possible that in the near future, we'll see more and more work getting pushed in that direction. So now, you know, that would be the part what I'd love to say. Happy to take any questions, although when you're listening to this, it's 2:30 in the morning in San Francisco, and I will hopefully be soundly asleep in my bed. So if you have any question, you can find me on the Bird app. Thank you very much.
Okay, thank you, Luca. And
good morning, everyone. I am Luca.
Okay, good morning, Luca. Okay, now we had a broader view from a really big company, and we discovered that they obviously have a more complex view of privacy that integrate with other aspects, and we will see that in the next years. But now is the time to create a secure system by ourselves with Antonio and Claudio. Please, come.
Okay, thank you, Walter. Okay, actually, we do not pretend here to build a secure system, but just to learn how to implement some of the techniques that we have seen before for a secure recommendation. Okay. So the ticker. Slide, sono scomparso. Okay, can you give me the slide, please? Okay, so if you have your laptop here, or if you want to explore something later, this is a QR code which connects to our repository, where you can also find the slides that we are showing. And it has also a link to Binder, where you can also right now follow with us this hands-on session and try with us to implement something. We will start with differential privacy in Matrix Factorization from scratch, and later we will attempt to see something related to secure multi-party computation with additive secret sharing and the same protocol in a more complex system like a recommender model. Okay, so.
Okay. So we start to try to implement from scratch a private matrix factorization with two different mechanisms: input perturbation with the Laplacian mechanism and gradient perturbation with Laplacian mechanism. The first part of this notebook is very, very simple. We try to import some stuff and some libraries that we are using the following. We install pandas, obviously, and matplotlib. Okay, and we use for this hands-on session MovieLens Small, last version of the smallest dataset that MovieLens provides. We download it from the online repo and save in our data. And obviously, we split the dataset in training and test part in order to use the training portion to train the matrix factorization and the test part to evaluate in the end the performance of these methods. Obviously, this is a sort of the example, so we don't have the, I say, the idea to provide the best performance is just of example. Okay, in this first part, we just have some provide this kind of data, and now we have the central core of this first hands-on, the class MF. The matrix factorization is one of the most simple approach to provide the collaborative filtering schema for item recommendation. In this case, we exploit the item and user latent vector and combine them with bias to provide the final score for the item. In this class, we initialize the embeddings P for the user and the Q for the item with a normal, with random normal, as usual with the name. This is for the user, so we have the number of user, and if I remember correctly, for the MovieLens Small is 610, and the number of factor, and in this case we declare ladder, and we can choose some of number. It's just a matter of developer choice. This is the same for the item perspective, so we can initialize with the random normal distribution the latent factor for the item, and moreover we set up the bias for the user for the item with a 0 vector, and the bias for the system as the mean of the dataset rating. So this is the simple matrix factorization approach. We also have two other parameters that we are useful for the next hands-on, and we will discuss in a moment. What more of interesting in this class? Okay, the training step for each epochs that we provide to the system, and for each number of interaction, we impose that the training step are the classical prediction of a combination of dot product plus the summation of the bias, and we estimate the error, and we use this error to update the factor of the user and the item regularized by the beta parameter, and the same for the embeddings. So this is a very, very simple training. Okay, in this part we have the train of Laplacian differential privacy, but we discuss it when we use in the following. In the evaluation part, we use the test set to evaluate the performance in terms of precision and recall. In this kind of scenario, we exploit the evaluation with the all rated items. So all the items that the user know from the training set are not considered in the final part. We test with only the test set for the user. It's important because, okay, we can now initialize and train our model with the 100 latent factor and learning rate 0.001 with, just for time is very strictly, 10 epochs, and the lambda regularization parameter 0.1. Okay, yes. Okay. So building the model and starting the training. Okay. Okay. These are the performance in terms of precision and recall at the top list at 10. So, is the base. Now, for the differential privacy part, we can start by analyze the process of the dataset, measuring noise version of this some global effects for the global average, for the item, and for the user. And finally, we can clamp these results. So the idea is to provide the original dataset, understand the sensitivity, and in this case, the sensitivity is the absolute difference between the maximum rating value and the minimum rating value in the dataset. And using this sensitivity, we can compute for the global, from the global average item point of view, the summation of all these ratings, and we provide to this summation an addition noise based on the Laplacian noise, obviously, that is scaled by the sensitivity and the number of the quantity, sorry, of the epsilon for the global average, scaled by the number of the ratings. Because the epsilon, the budget of the differential privacy, could be distributed across this kind of factor, let's say. In the following, we say that the entire budget of differential privacy is split in two different portions. One for this global effect and one for the standard training with differential privacy. So we have this global average item, and we exploit also the item perspective for the mean to obtain the global average also for the user with the same in the same way. In this case, we sum the training, and we provide an addition factor, noise factor based on a Laplacian noise. Also, in this case, we scale the scale of this Laplacian is based on the sensitivity and the portion of the privacy budget dedicated to this. And also for the user, we can provide these user factor that are the, as we can see at the beginning, the global effect related to the user. In the end, to sum up, we preprocess the data, exploiting these effects, user and item effects, and we provide as in the end of this function, the preprocess rating, the effect of the item, and the effect of the user. These are the functions that privatize the global effect, and we apply this function with this parameter. As I mentioned before, we have the budget, the global budget, the entire budget, privacy budget, 5, and we split this privacy budget in this way. We use 0.3% of 13%, sorry, of this budget for the global effects for the user and for the item with this factor, and the remaining part, the 70% of the epsilon, is used for the training. This parameter coming from the Friedman work. Okay, now we pre-process the data. Okay. Maybe it's okay. Yes, okay. So in this part, we try to perform the first tentative to provide some differential privacy to our model and provide the input perturbation. We use the 17% of the remaining part of the budget. We exploit the training set preprocessed in the previous step. And with this function, we try to also adding for each ratings the residual budget of privacy in the same manner that we've seen before, and we clamp the results between a factor, and we use this trained set perturbed to train our classical matrix factorization model, and we obviously try to evaluate. Okay. As you can see, the performance are different since before, and in this case are very, very low with respect to the previous plain trained model. And the result is that the privacy maybe is very strict in this case, so we have to increase maybe this budget to provide more comfortable, let's say, metrics from this kind of point of view, but it's a matter of the development of the model. We also train to the same matrix factorization, but in this case we use the train Laplacian differential privacy training strategy that, just very quickly, try to add to the error that we compute time to time during the computation a Laplacian noise. And this is the function. The idea is very simple. We can provide also the prediction in the same way, and we compute the error. We add this noise, and in this case, for each epoch, we scale the sensitivity by the epsilon, because for each step, we scale this noise by the epochs and the sensitivity, and scale by the epsilon at each epochs, because for the composability theorem, we split the privacy budget for the number of the epochs. And we can try to impose also a maximum error to clip this error in order to stay in the same range. Also in this case, we can evaluate the performance, and also here the results are different from the plain original model, but we can try to investigate better about the budget dedicated to this data set to obtain some interesting, let's say, results. So the next part is just a proof that we can use a various value for the epsilon budget, and across this value, the results change and increase in terms of performance. So I leave the stage to Antonio for the last hands-on. Thank you.
Okay, thank you, Claudio. Okay, so you will see in this repository that we also have a second notebook in which you can experiment, more or less the same approach, the second approach that we have seen right now, so the differentially private stochastic gradient descent, but by using this TensorFlow privacy library. It's very simple. You have just to use this new function instead of the classical functions that we use to train to optimize the model. So just for your interest. Okay, in this second part. Okay, in this second part. We will try to implement a very simple secure multi-party computation model just to reproduce the example of the beers. Okay, so we are talking about the additive secret sharing model. Okay, the way we use for the implementation of secure multi-party computation is to randomly generate some numbers. If you remember, for example, Bob had to split his secret into 3 shares. Okay, so in this case, we generate randomly 2 shares, and the remaining one is just obtained by subtracting the other 2 shares from the original value. But we do that in a finite field, for example, by defining a very large prime number Q that acts as a modulus. So this is the encryption function, the one that I was describing. So this is a very large number, and then we have that. In order to encrypt X, we have to generate n shares minus 1 shares. And then we can, of course, in the range 0, Q. And then we can obtain the final share by subtracting the sum of the share modulus Q from the original value. So let's try to encrypt 100 by splitting it into 3 shares. And these are the 3 shares of 100, of course, in this finite field and with those random numbers. In order to decrypt this number, of course, we have to sum the 3 shares that are pieces of information, meaningless pieces of information, sum them, and compute the modulus Q. Okay, so let's suppose now that we want to reproduce the example that we have seen before. Okay, so we have 3 secrets. So here the number of beers has increased, but that's okay. So 100, 200, and 300. So these are the private values that we have. So the idea is to call the encryption function. Okay, and these are the local shares of those secrets. So the first list is the list of the share of the first secret, the share of the second secret, and the share of the third secret. So this is the list of numbers that right now is in the device of Elise, for example. And this is the list of number in the device of Bob. Okay, so as I was mentioning before, each party has now a piece of information about itself and the other 2 parties. So how to compute the sum of the 3 secrets? We just sum locally the shares that we received, here. Okay, and now each party has a share of the sum of the secrets. So now we can decrypt the final secret, so the sum of the initial secrets, with the function that we created above. So we have just to call the decryption function. Okay, this is the average because we wanted the average. So 200 is the average of 100, 200, and 300. Okay, to implement the multiplication, we should use the SPDZ protocol that we mentioned before. And with this protocol, okay, here you can see just a more structured version of what we have seen right now. So we distinguish private value from public values, okay. But the interesting part is that we had here this multiplication part. These are 3 numbers that are generated by a crypto provider. These numbers are subtracted by the original values and then distributed to the parties. And then you can convince yourself that by performing this kind of operation, you will obtain a new private value that is the multiplication of the 2 private value that we have before. All these stuffs are computed on the shares of the secrets. So each time we have to exchange among the users all these shares in order to perform a computation. So that's why I was saying before that SMPC is a very good technique, but it requires high communication costs. Okay, and now just to conclude, since we have only 2 minutes, in the fourth notebook, you will find the same approach, but this time applied to neural collaborative filtering in securely aggregated vertical federated learning. I say too many words, but I will try to explain now. So the scenario is this one. We have 3 organizations. Each one has some data that doesn't want to share to the other parties, but they want to train a collaborative filtering model in a joint fashion. They decide to use federated learning, and we call it vertical federated learning since they have data about the same users but different items. So I am an organization, I have some items, and here's another organization has some other items, but we have some users in common, so we want to train this joint collaborative filtering model. So this is the scenario in which we can apply vertical federated learning. And in this case, since, as Walter was mentioning, we know that federated learning could be not so secure as we expected some years ago, we decide to apply secure multi-party computation. So we compute our gradient locally, because we receive a global model, then we use our data to train locally this model, and then now the 3 parties have 3 different gradients of the parameters. So now they have to merge them. So basically what we want to do, and what we do usually in federated learning, is to compute the mean of these parameters. And as we have seen before, we can use, of course, secure multi-party computation to compute the mean, the average of 3 secrets. And in this case, the secrets are, of course, the local gradients. I don't know if this scenario is clear. And if you look at this notebook, you can see that, okay, we split the with the same users but different items for each organization. And then we use this interesting library, which is called PySift, with its integration that is called Sympathy, I suppose they call Sympathy, SciMPC. Thanks to this library, you can perform complex computations on the secrets, because they implement SPDZ protocol, but also this Falcon scheme that provide also a malicious security guarantee. And then here we have, as before, the training of a normal federated learning model. While here you can see the training of the same federated learning model, but with all the secure multi-party computation stuffs, with which you can compute the mean of the 3 secrets. And I repeat, the secrets are the gradients, the local gradients. And in this case, I won't run this part because we have to download Torch, and it's very huge. But you should see the same results both in the unsecure version and in the secure version, because this time we are using cryptography that does not sacrifice accuracy, but you will see a huge increase in terms of computational time, in this case, because we are just simulating in one machine the communication part. But that refers above all to this communication overhead. So if you have any question, we are here, or you can ask us offline, I think, also. Yes, after the wrap-up. And okay, I give the stage to Walter to conclude this tutorial. And thank you for attending.
Okay. First of all, I would like to thank all the other authors of this tutorial, because without them, it would not be here, basically, all the tutorials. So a big thank you to all of them. And as was mentioned before, all the material will be made available, also the recordings, and the slides should be online right now, and all the collabs. For what regards the question, we will come back in a moment with the questions. And finally, I want to say to you and to the remote audience that we know that this tutorial was really, really dense, and there is a lot of math and a lot of maturity in the community. And we consider it necessary, since in the last years there was like a confusion. And I think that you have seen in the papers that we have presented, some in the 2028 or 2020, they didn't know what happened a couple of years before, or just the 1 year before. So we tried to dissipate this kind of doubts, and we did our best, basically. And finally, since we know that it was so difficult to stay with us for all the time with all this math, I would like to thank you all from our side. And that's all for this tutorial. So now we can move with who is interested in it for the questions. Thank you. If there are any questions, obviously. Come here.
Thank you.
Come on the stage, Manel. Oh, we are recorded. Oh,
So my question is related to the differential privacy. Again, we know we have the user item matrix. And let's say we have those M features, items. And we want to protect users, I don't know, maybe with federated learning. How do you do? Is it exponential or Laplacian? Which noise do you choose to add for the context of recommender system? Do you personalize this budget per item? And if so, is this personalization, how this personalization applies to the users?
Okay, thank you, Manel. Okay, actually, since in this kind of algorithms we use real numbers, usually some Laplacian noise or Gaussian noise is injected, so Laplacian or Gaussian mechanisms are used. And as for the question about the privacy budget, okay, there it depends, of course, on the paradigm you are using, because when you are using federated learning, for example, each user has to share her data or her gradients to the aggregator, and in that case, maybe you can also decide on yourself your privacy budget. But their privacy budget usually is not used item-wise, let's say, but it's something, as we were saying in this Matrix Factorization tutorial part, this budget is applied, let's say, epoch per epoch. So in each epoch, we sacrifice some part of our privacy by applying this Laplacian noise or Gaussian noise to the gradient or to the data. Of course, it depends, because each situation is different. If you apply to the data, is highly different with respect to the situation in which we apply differential privacy to SGD. So in the case of SGD, we should measure how much a single rating could affect the value of the gradient. And in that case, we show in the notebook that each rating could affect the gradient with a maximum of delta R, that is the maximum and the difference between the maximum and the minimum of the rating that we can have. But for example, in this case, we are protecting just the value of the rating. In some cases, for example, we would like to protect the presence of a rating, and it's a different task. And in that case, the sensitivity has to be computed, and you have to analyze how much, for example, the presence or the absence of a single rating affects, for example, the gradients, if you are applying noise to the gradients. But it could change if, for example, we want to protect the presence not of a rating, but we want to protect the presence of a user in a certain data set. Then, in that case, we should consider the sensitivity that a user has on the whole algorithm, or on the whole weight of the network, for example. So I think it's basically, for this differential privacy, it's basically a matter of understanding what we want to protect and which is the value of the sensitivity. And then you are done. You have just to choose the mechanism that fits best with your needs. I don't know if I answered.
Yes, and you raised another question for me. So,
okay.
We know there is an interactivity between users. In a sense, there are some nearest users to you. So if I will apply the noise to a user, I want to protect the presence of the user. This is your point, the last one. So either I can protect the sensitivity of the rating, looks good. Okay. And now if we go to the protecting the user, if I will apply the perturbation, this noise, would I need to take into account the nearest neighbors' users? Or should I just take and apply the perturbation separately to the users? If you see how I think, it's kind of similar to my previous question when I mentioned, should I apply the noise per feature? And I don't take into account that there is a coherence between the items. So now the same thing. We know that there is also coherence between users. Is this will be maintained or destroyed? Or is it important from your opinion? Of course.
Yeah, it's important from my opinion. And as for the destroying the coherence, I think that it could depend on the amount of noise that you are injecting. But as for the question of should I take into account the fact that there are some neighbors of some users, well, in that case, it's an interesting point, and maybe it should be still studied. Again, in this case, I would think to the sensitivity in the sense that maybe the fact that a user is present or not in the dataset does not affect just the gradients, for example, the weight of the network, but also affects the data of another user. So also in this case, I would say that it's another kind of sensitivity, let's say, and it's an analysis that should be interested to be performed. Yeah, thank you.
Okay. Okay, thank you all, and now we can go to have a lunch together.